dioxide, iron, manganese, and sulfur collect in these dips. One of the largest is known as Lau's Bath. Near Palisades Point in the Northeast Basin, more warm pools cluster in another active zone. Standing among these vents and pools are mineral towers built by the slow buildup of dissolved minerals from the vent fluid. Some reach over 30 feet tall. They look like chimneys built by a process that is still going on. This is not what you find at the bottom of an untouched mountain lake in Oregon. This is what you find at the bottom of an ocean, near a mid-ocean ridge where the Earth's crust is pulling apart. The heat driving these vents is active energy from the same magma system that built and then destroyed the mountain this lake replaced. Research at these vent sites has continued for over 3 decades. More recent work has found unexpected variety in the bacterial mats, finding communities far more complex than anyone predicted. The organisms are not just surviving. They are building a living system powered entirely by volcanic chemistry. The vents are not shutting down. They are keeping life going. Pay attention to this next detail, because it explains everything about why Crater Lake exists. Roughly 7,700 years ago, a towering volcano called Mount Mazama stands where the lake is now. Its summit reaches roughly 12,000 feet. It has been building itself through eruptions for over 400,000 years, stacking flows of volcanic rock one on top of another. The Klamath people, whose homeland includes this region, carry a spoken history describing a world-ending battle between sky and underworld spirits that results in the destruction of the mountain, a story now understood to be a remarkably accurate eyewitness account passed down through roughly 300 generations. Then Mazama erupts in a way that dwarfs almost anything in the geological record of the past 10,000 years. Roughly 50 cubic kilometers of magma, about 50 times the volume that Mount St. Helens threw out in 1980, blasts out in a single devastating event, rated 7 on the Volcanic Explosivity Index. Pyroclastic flows, superheated walls of gas and rock, race outward from the collapsing summit and travel up to 70 kilometers down every drainage. Ash rains across 8 American states and 3 Canadian provinces. The eruption column punches into the upper atmosphere, and the resulting ash layer is so widespread that scientists across the Pacific Northwest still use it as a time marker in layers of soil. If you dig into the ground anywhere from southern British Columbia to northern Nevada and find a pale gray band of volcanic ash, there is a good chance you are looking at Mount Mazama. And then the mountain collapses. Without the magma holding it up, the summit caves inward, dropping thousands of feet into the void. What remains is a caldera, roughly 8 by 10 kilometers across, and over 1,000 meters deep. Over the next few centuries, rain and snowmelt slowly fill the bowl. No rivers, no streams. Just rain and snow, building up year after year until the water reaches a steady level. That process is still happening. The same magma chamber that powered Mazama's destruction still sits beneath the caldera floor. It is cooler now. It is not making the kind of magma that could fuel another massive eruption, at least not on any timeline that matters to humans. But it is still there. The hot water vents prove it, so do the warm pools. And the bacterial mats feeding on volcanic chemistry nearly 2,000 feet underwater leave no room for doubt. And the earthquakes prove it too. After that first detection in October 2013, more seismic events follow. In April 2014, roughly 20 volcanic earthquakes show up on the network at depths of 5 to 10 kilometers. In May 2015, 4 more. Then, in June 2020, a magnitude 1.3 earthquake strikes directly beneath the lake itself, near Dutton Cliff on the southeast rim, at roughly 2 kilometers below sea level. 24 aftershocks follow over the next 12 hours. This is the first time the network records a clearly located earthquake beneath the water surface of the lake. The official assessment of this activity is that it is more or less normal for the volcano. That's not a typo, by the way. More or less normal. Because while the earthquakes are small and consistent with background volcanic activity, the network picking them up has only 4 stations. 4. For a caldera, 8 kilometers wide, holding 5 trillion gallons of water, ranked the 17th most dangerous volcano in the entire United States. Compare that to what sits on other Cascade volcanoes at the same threat level. Mount St. Helens, ranked number 2, has dozens of earthquake stations backed up by ground shift monitoring, gas detection equipment, and a fully staffed watch center with direct line of sight to the crater. Mount Rainier, ranked number 3, has tilt sensors, real-time ground shift monitors,